Hey everyone, Katrina here. Today we're going to talk all about trigonometric substitution and how we can use that to solve rational integrals. Be sure to watch to the end to see the example unfold, and please subscribe for more videos. Let's dive in. So when we're looking at trig substitution, there's three main cases that we want to consider. And we'll go through all these cases in detail today, and we're going to explore an example using one of these cases. So you might ask, which case, do we use? So the case that we use depends on our integrand. So how our integral is set up is going to determine which trig substitution will be applicable for our specific problem. So the whole goal of using trig substitutions is that we want to use all these amazing properties that trig functions have to help us eliminate unfavorable or difficult situations, such as the root of f of x or f of x to some power. So we know there's a lot of different properties and identities that go along with trig expressions. So that's really what we want to use to see if we can simplify our problem. So we're going to go and look at our three different cases right over here. So our first case is as follows. So if our integrand contains the square root of some a squared minus x squared, then as a result, we're going to want to try the following trig identity. In particular, we're going to want to try x equals to a sine theta. Okay, so x equals to a sine theta, where this a here corresponds to this a over there. Our second case is if our integrand contains the square root of a squared plus x squared, then we want to try that our x equals to a tan theta. And lastly, if our integrand contains the square root of x squared minus a squared, then we want to try x equals to a secant of theta. So these are our three cases. So make sure that you write these in your notes, because this is a really great cheat sheet for you to have, especially when you're trying to tackle a difficult rational integral. This can really, really help you out. However, we still have to consider that there's some caveats that we have to keep in mind. We can't just use them freely. We have to be sure of a few things. So our first caveat is that our a value has to be positive. It has to be greater than 0. And we also have certain conditions that we need to impose on our angle, on our theta. So each one of these conditions corresponds to the previous substitution that I showed you. So this number 1 over here, where theta has to be between negative pi over 2 and pi over 2, that corresponds to our first substitution here with our sine theta. And then our second one over here, same condition, where theta is between negative pi over 2 and pi over 2, that corresponds to our tan. So I'll write that out for us. So the first one corresponds to the x equals to a sine theta. Our second one here corresponds to our x equals to a tan theta. And then our last one over here, our last caveat, we have two different options for a domain for this one, and this corresponds to our last substitution, which was the x equals to a secant theta. So these are just good caveats to keep in mind while you're doing your trig substitution to ensure that you have a result that makes sense. So now that we have all the housekeeping out of the way, let's go ahead and jump into an example. If you're enjoying the video so far, please give it a like and subscribe for more videos. I have much more calculus coming your way. Okay, let's look at our first example. So we are considering the following integral. We have the integral of 1 over the square root of 1 minus x squared. And we're integrating with respect to x. Okay, so we can first see that this is a rational integral. So that's going to be a little bit challenging to solve. We can't just apply a rule directly right now and get the answer in one step. We can see here that we have a square root sign, which also complicates things a little bit for us. However, this is looking pretty similar to some of our earlier substitutions. So let's go ahead and recall our first substitution here with sine. Look at this one right over here. If we have the square root of a squared minus x squared, we can use this substitution. And that seems exactly what we have over here. So in this case, we can see that our a value is equal to 1, and then we have our x squared over there. So we can write our a over here. So because of that, we can use our sine substitution. So let's go ahead and write out our substitution. So recall that it's not necessarily guaranteed every time that these work. That's why we use a quote-unquote try. Most of the time it will, but just be aware that in some situations you might have to try a few other tools as well. Here, exactly. So we are going to try that x equals to a sine theta. And in this case, a equals to 1. So that means our x equals to sine theta. And now we have to remember our dx over here. So if we take the derivative of x, which is equal to sine theta, then that means that we have cos theta d theta. Perfect. So now we can use these two terms here for x and dx and substitute it into our integral over here so that we can now solve it. So as a result, we have the integral of 1 over the square root of 1 minus sine squared theta, and then we have to multiply this by our dx value, which equals to cos theta d theta. Perfect. So now we have to look at what we have underneath our square root. So we have 1 minus sine squared theta. But this is actually an identity that we can use. This over here is our Pythagorean identity. So recall that cos squared theta plus sine squared theta equals to 1. So if we go ahead and rearrange this equation, we now have that cos squared theta equals to 1 minus sine squared theta. So that means we can substitute cos squared theta for this entire term right over there. So as a result, we end up with the integral of, what do we have here? Cos theta divided by the square root of cos squared theta d theta. Okay, so the next thing that we can do is we can simplify this expression. So, sorry for that, my computer just glitched momentarily. So since we have a square within a square root, we can simply take the absolute value of this. So what I mean by that is we have the integral of cos theta over the absolute value of cos theta. So essentially what we did there is we just took the positive value of the square root over there. And remember, we're still differentiating with respect to theta. So because of our restriction on our angle, we have to assume that our cos theta is going to be greater than 0. Because recall, in order for this to work, we have to have theta between minus pi over 2 and pi over 2. This was one of the caveats that we had. So when we are looking in between this, when we're looking between this domain for theta, we can see that cos theta is going to be greater than 0. Because cos theta is positive on this interval for theta. So as a result, we can get rid of these absolute value lines for cos. So that simply means that we have cos theta divided by cos theta d theta. And I think we can see where this is going. So this is simplifying quite nicely. So this will simplify to 1 multiplied by d theta. And this will end up with a really nice integral that we can solve very easily. So this is simply equal to theta, and then remember we always have to add plus c, because this is it's not a definite integral, it is an indefinite integral. So that means we do not have integration bounds, and because of that we always have to add this plus c. So always remember that for your exam. And the last thing we have to do is we can do the substitution. So we know we have the answer that we have theta plus c. However, this problem was with respect to x. So how can we convert it back into x? So this is where we have to recall that x equals to sine theta. This was our initial substitution. So how can we rearrange this? Well, we know that arc sine of x is going to be equal to theta. So there we go. So that means that the final answer equals to arc sine of x plus c. So always remember that when you do substitutions, you have to substitute back in the last step. We have to go back and rearrange our equation so that we have our equation isolated for theta, and then we need our final solution to be with respect to x. That's very important. Well, I hope you enjoyed this video today. You're learning great knowledge. This is for about Calc 1, about first year university. And these tricks will allow you to solve very challenging integrals and rational integrals that might not seem so clear when you first see them. So if you ever see these 3 forms that we talked about today, make sure that you're doing your trig substitution, and that will help you get to the answer. And anyways, please subscribe for more videos if you're enjoying this one, and please feel free to comment any questions that you have or request any other videos that you would like to see in calculus or in other areas of math. And with that, I'll see you next time.